Hallo, hallo, hallo. Good morning. Welcome to the second day of Strings 2022. Before we start, some small announcements. So if you don't want to store small bags in the office over there, there's a small bag storage room just opposite the auditorium. It's free of charge, but you need a €2 coin to insert and you get it back after your bag. And you can only store bags there during the day, so please don't use it as an overnight storage. There are also workspaces in the hallway, so if you exit the auditorium and turn left, go towards the end of the hallway and then turn right where there's the ATM sign, then you have some workspaces available. And there are 2 additional rooms that we have, one quiet room. There will be signs up in the coffee break. You continue this hallway, go downstairs, go upstairs, turn right, and then it's seminar room number 1. That's the quiet room. And there's a work room available as well. It's seminar room number 2, which is one corridor further. Again, there will be signs up there in the coffee break. And speaking of the coffee break, so in the next coffee break, the conference office will be occupied for an interview. So please don't go there in the first coffee break. If you have something there, retrieve it during the lunch break. Okay, and with that, I'll hand over to the chairman of the first session.
Hello and welcome. After a great first day of talks, we are good to go again. So the first speaker of the day is Andreas Karch, and we'll be hearing about Randall-Sundrum, Branes, and Holography. So over to you, Andreas.
Thank you. Thank you very much to the organizers for inviting me here to give this talk. No, it's a great pleasure to participate of what we learned is sort of the Olympics of physics. I was tasked to review Randall-Sundrum branes and their applications to holography. And you should be aware that the original Randall-Sundrum paper had made quite a splash in its day when it came out. But this is sort of physics from the last century, right? What this will mean is that the first half of my talk, I'll talk about papers which are sort of 15 to 20 years old. Now, I know what you're thinking, but no, please bear with me. This is going to be interesting. I promise you in the end, we're going to have applications to things people actually care about today. So let's get started with a very basic Randall-Sundrum setup. Essentially what Randall-Sundrum is like a very simple exercise in general relativity, where you're trying to find solutions to Einstein's equations, where you have like an action which has the Einstein-Hilbert term, a cosmological constant, and the only matter you add to Einstein gravity is a soap bubble, right? We have a brane, it has a tension, and its action is that it wants to minimize its world volume. You can do this in any dimension, but for this talk, I'm always going to work with like a 5-dimensional bulk and a 4-dimensional brane. And I'm going to work with a negative cosmological constant so that if it weren't for the brane, my solution would be radius 5 with curvature radius L. So the first thing we have to wonder about is how do we solve the equations of motion when I have a source like this, right? The source is basically a delta function localized. I have a 5D Einstein equation, but I have a source that only lives in 4 dimensions. The way you do this, I best want to explain by an analogy that probably all of you have seen in your undergraduate days. That's how do you solve Schrödinger's equation when you have a delta function potential. It's exactly the same thing. You have a source which is sort of codimension 1, right? So the way you would deal in quantum mechanics with a potential like this is you go in and say, well, away from the potential, there's just nothing. I'm solving like empty space, free Schrödinger equation. So my solutions are exponentials, even like real exponentials if I'm looking for bound states, plane waves when I'm looking for scattering solutions. And then the way the potential shows up, because it's a delta function, you don't actually ever want to solve the equations at 0 directly at the location of the potential. You take Schrödinger's equation, you integrate it across the delta function, and then instead of getting a potential, what you get is you get sort of the jump equation. The second order differential equation that was Schrödinger's equation becomes a condition on the jump in the first derivative of the wave function, where the strength of the jump is given by the coefficient of the delta function. See, we're going to do the same with Einstein's equations. We're going to go back in and say, well, away from the brane, I have nothing other than the cosmological constant. If I'm looking for vacuum solutions, then away from the brane, I'm going to get radius 5. So my solution is going to be made out of gluing together like little bits and pieces of radius 5. But I glue them together in sort of a discontinuous way. I need to kind of glue them together across the brane, and to see what's happening, I take Einstein's equations and I integrate it across this delta function source.
The micro turned off. Just a second.
Looks on.
Okay.
Okay, so I integrate Einstein's equations across the brane, and then you get what people know as the Israel equation, which is saying that the metric is smooth, but the extrinsic curvature jumps. The extrinsic curvature is sort of the first derivative of the metric, the analog of psi prime in our Schrödinger equation example. And you find that the jump in extrinsic curvature across the brane is proportional to the stress tensor of the brane, which for our soap bubble is basically just proportional to the induced metric. So the Israel equation is saying the jump in extrinsic curvature across the brane is proportional to the induced metric. So this way you get what's sometimes known the full RS spacetime, sometimes known as the full RS spacetime, which would be sort of two identical copies of a part of ADS5 glued together along the brane. You have a C2 symmetry, which exchanges the two sides. For most applications, it's kind of cumbersome to think of this complete two-sided geometry. You can simplify the spacetime by imposing some sort of orbifold condition, where you say, I want to throw away all odd modes, only keep the even modes, and that way you end up with a single part of ADS5, one of those two copies, and it ends on this brane. Right? This makes this brane an end of the world brane. I think back in the days people didn't use that word, but this is how we would call it today. How this brane actually looks like depends crucially on the parameter lambda, the tension of the brane. I'm always going to work with positive tension branes. If you have negative tension branes as well, you would put absolute values in these equations. And you can think of this table as there being some sort of competition. There's some negative energy density from the surrounding ADS5. There's some positive energy density from the tension of the soap bubble. And if you tune them just right, there's a critical value which depends on the number of dimensions you're in. Then you end up with zero cosmological constant on the brane. The brane has a flat world volume. Sometimes people call this the critical or the Minkowski RS brane. If you have too much tension, you end up with a de Sitter space on the brane. If you have too little brane tension, you end up with an anti-de Sitter brane. If you want to see pictures, so here are pictures in Euclidean ADS, or equivalently, you can think of them as being a constant time slice through global ADS. Then you find that these branes look actually very different, right? So this is the de Sitter brane, is sort of some hyperboloid that's sitting inside ADS. So in the Euclidean case, it's just some sort of sphere. The Minkowski brane sort of touches the boundary at a point, and the ADS brane looks like really different in the sense that it genuinely intersects the boundary, right? This depends all on this parameter lambda c. A few more words about these pictures. So in all my pictures, I'm always going to have a shaded region, which is the one that's being removed, and the white region is the one that's being kept. That's what you need to do for positive tension brane. If for any reason you might want to include a negative tension brane, you get the same pictures, but the role of what's kept and what's thrown out would be reversed. So positive tension branes, for me, I throw away the purple region. The full RS spacetime would be two copies of the white region glued together on the brane. But in my talk, I'm mostly going to focus on this orbifolded case where we only keep the white region. And then last but not least, often it's more informative to study this from the Poincaré patch point of view. So in this case, you could sort of zoom in on the region. Then I get my standard Poincaré patch representation of ADS, where I have a brane that's parallel to the boundary. I remove the UV part. I keep the IR part. These two guys, the Minkowski brane and the de Sitter brane, they're really what Randall-Sundrum is mostly about for almost everybody not in this room. Right? These two branes, they had like numerous applications in phenomenology, in cosmology. I think the buzzword here is that Randall-Sundrum branes geometrize hierarchies. If you want to explain huge hierarchies, exponentially large separations in energy scales, you can translate this into geometric properties of where these branes are located in ADS. I'm not going to talk at all about this, right? This is for a different community. What we're going to talk about is almost entirely the subcritical ADS brane. A subcritical ADS brane, again, is the one that intersects the boundary. This is how this looks like in the Poincaré patch. And what's going to be interesting for us is that the ADS brane is basically removing part of the boundary, but it keeps the other half of the boundary. And we'll see that this leads to many, many interesting applications. It will give us an ADS DFT representation of field series with boundaries. It will give rise to something which we call double holography, and massive gravity will play a very crucial role in the setup. But before we get there, I wanted to say a few more words about the critical brane, because the critical brane will teach us two more important aspects of Randall-Sundrum branes. The critical brane will teach us about localized gravity, and it will lead us into kind of how to interpret Randall-Sundrum branes holographically. So this will lay the groundwork for our discussions of the subcritical case. So far we studied vacuum solutions. The next thing which we want to do is we want to study linearized fluctuations. around the vacuum solution. Linearized fluctuations, you solve linearized Einstein's equation, some second-order differential equation. You can do this analytically, but the easiest way to present the results is you change variables until Einstein's equation just looks like a Schrödinger equation. And I'm going to plot for you the potential. That's how people actually solve this problem. It also makes it very intuitive for a physicist of what the spectrum looks like. So if you do this for like linearized fluctuations around the Minkowski brane, around the critical brane, you get something like this. People call this the volcano potential. You get like a 1 over r squared peak here that comes from the fact that the bulk is ADS5. This is sort of the ADS5 horizon down there, the IR of ADS5. You get a 1 over c squared potential. It would rise all the way to the boundary, but then you hit the brane that sort of cuts off the thing and has some delta function crater sitting at the position of the brane. So if you look at the spectrum, you get a continuum of modes that comes all the way down to zero energy. And again, you should think of those modes. They're basically mass squares of the 4D gravitons. If you do sort of a KK decomposition of the 5D fluctuations. So you have a continuum of modes, comes all the way down to zero mass. And on top of this, in this delta function crater, you have a localized massless 4D graviton. So we have massless 4D gravity trapped on the brane, giving rise to naively a 4D Newton's law on the brane, even so I have a non-compact dimension. You might worry that this continuum of modes, which comes all the way down to zero mass, sort of pollutes the 4D force law, but that isn't the case for matter sources on the brane. The light KK modes, they have like wave functions that are vanishing near the brane, meaning they couple very weakly to matter on the brane. So matter on the brane almost doesn't couple to the light KK modes. The heavy KK modes, they couple order 1 to the brane, but they're heavy, so they only correct Newton's laws at like very short distances. So this way you get like a 4D force law from this 4D graviton trapped on the brane, and that's why this is often termed an alternative to compactification. It's a different way of getting 4D gravity out of a 5D spacetime. This also gives some very interesting way of thinking about this brane from the point of view of holography, right? We're having pieces of ADS5, so you somehow want to interpret this in terms of CFTs. This is sort of the level at which I'm going to use ADS CFT. We all know that gravity on ADS5 is like equivalent to a 4D CFT on the boundary. And the radial direction in the bulk is the scale in the CFT. So let's try to apply this to this brane, right? So the spacetime that I described to you so far, the solution we found describes 1 or 2 copies of the IR part of ADS5, depending whether you're orbifold or not. And they're glued together along this 4-dimensional brane, and there's a graviton trapped on the brane. So let's take these words and translate them one by one into a sort of ADS language. There was a conference in Santa Barbara where sort of many people came up with this idea. I think these are probably the 3 people mostly get quoted for this. But I think this idea was sort of around in the air, where people say, well, no, I have pieces of ADS5, so these are like 2 if I take the full RS spacetime, 1 if I study the orbifolded version. But one way or another, I have a 4-dimensional CFT. I threw away the UV part of the geometry, so I somehow put a UV cutoff in there. And I look at this, and the red and the blue has no sign of a localized graviton, but I know it's there in the 5D description. So presumably I need to add dynamical gravity by hand in the holographic dual. So the holographic dual that was sort of conjectured for this is that you actually have a holographic dual which as always involves a 4D CFT, but you need to by hand add gravity back in the holographic dual. So you have a 5D geometry as a 5D graviton is dual to a 4D CFT plus a 4D graviton. Gravity is part of the holographic dual. This sounds like a big thing to swallow, hard to believe, but there's at least some justification of this out of string theory. We'll do much better later for the subcritical branes, but for the critical branes, this is, I think, currently the best version to embed this in string theory. This is due to Hermann Verlinde, where he said if you want to do this in string theory, what you should start out with is some sort of F-zero compactification, which is really type to be on a 6-dimensional base. And by anomaly cancellations, you have to throw in some decently large number of these 3 branes onto this, right? This n can't be taken to be infinities given by some geometric data of the base. But there's some reasonably large number of these 3 branes that you can put on the space, and they're moduli that move these 3 branes around. One thing you can do is put them all on top of each other. They back react and you get a geometry where some ADS5 times S5 throat, a finite piece of ADS5 times S5 gets sort of pulled out of that base. But then if you go towards the UV of this ADS5, you find that this ADS5 stops, and instead you run into a Minkowski force space times the 6-dimensional internal base. And that that has dynamical 4D gravity as part of the full description, but you seem to have this sort of the low energy physics is given by the geometry of ADS 5 times S5. So this is supposed to be how this looks like in string theory. This will already be our first indication, right? When people study Randall-Sundrum branes, these are not the branes that you're familiar with from string theory. These are not D-branes or things like this. They're toy models for something more complicated, right? This would be one of these more complicated things. The problem with branes in string theory is they source dilitons and two-form fields and all kinds of other fields, and Randall-Sundrum branes are really just soap bubbles, and we tend to not have those in string theory. But Randall-Sundrum branes are sort of bottom-up models that can teach us valuable lessons, which we then should check in top-down embeddings. Okay, time to move to the subcritical branes, right? So let's do the same exercise of trying to understand holography for these branes for the subcritical case. Right? Sort of what's new in the subcritical case is that we keep half of the original boundary of ADS5. So I take ADS5, I used to have n equals 4 super Young mills, say, on all of Minkowski space. I keep n equals 4 super Young mills on half space, but on the other half, I cut out the real boundary, and instead I introduce the brane. Let's first use the same words that we used in the critical case and try to interpret what happened here, right? So I have this piece of n equals 4, this piece of n equals 4 super Young mills I just keep. I have n equals 4 super Young mills on half space. Then I have n equals 4 super Young mills on half space again. Half Minkowski space is conformally equivalent to ADS4, but once I kind of introduce a cutoff in the CFT, it actually matters. And in this case, we have n equals 4 super Young mills on ADS4. There's some sort of UV cutoff because I threw away this shaded region, and I have to add a 4-dimensional graviton by hand. So you get one sort of putative dual description for this, which would be saying this Randall-Sundrum geometry is dual to a CFT on half space, a CFT on ADS4. The CFT on ADS4 is coupled to dynamical gravity. And in addition, those two talk to each other by some sort of transparent boundary conditions across here, right? I can clearly, from the 5D point of view, send signals from the blue brane to the red boundary. So one way or another, they communicate via boundary conditions at this common boundary there. People often ask me, what do you exactly mean by transparent boundary conditions? Transparent boundary conditions, to me, this is like non-elephant biology. The only thing I tell you what this is not a completely reflective boundary condition. There are many, many different transparent boundary conditions. All I want is that there's some way for energy to come from the blue brane to the red boundary and the other way around. Okay. In a second step, you can go in and say, well, now I have gravity on ADS4. I know something about gravity on ADS4. It's dual to a 3D CFT. So there's a second step in the duality you can do here. There's a second dual description of the setup where you just have n equals 4 super Young mills on half space coupled to some non-trivial 3D CFT as a boundary condition. So you have a second description of this whole setting in terms of a BCFT. In fact, that suggestion has been made twice, right? There are two papers out there in the literature which say if you want to study the dual to ADS-CFT with a boundary, what you should do is you should put a brane in the bulk that solves Israel equations. Those two proposals are identically at the technical level. The one difference is sort of the philosophy. What was in our papers, what I just described to you. Takyanagi thought of these Israel conditions more as a Neumann boundary condition for gravity, but no, it doesn't matter how you think about it. It's in the end the same equation. The other difference is 10 years. Actually, this has led to the effect that many things have been done twice in the literature. You might think the first thing you want to calculate, if you have a new dual descriptions, you want to calculate correlation functions. So with Stan Friedman, Oliver D. Wolf, and Ofer Aharoni, we calculated sort of the Witten diagrams for 2-point functions in this BCFT. In the BCFT, the first thing you want to calculate is a 2-point function, right? An ordinary CFT. 4-point function is where all the interest lies. In the BCFT, you get interesting things already at the level of the 2-point function. We calculated all these Witten diagrams, and it looks good. You find that diagram by diagram, they obey sort of the theorems that the correlation functions in the BCFT should obey. We also found that the structure of a BCFT is hidden in a encoded in a very nice way in the fluctuations in the bulk. If you do this Kaluza-Klein mode decomposition that I described to you before, you find that this mode decomposition corresponds exactly to what's known as a boundary operator expansion in the BCFT. The basic operator expansion in the BCFT is simply the mode expansion in the bulk. 15 years later, Leonardo and his collaborator calculated the same Witten diagrams again. Fortunately for us, the results hadn't changed. They came still out to the same numbers 15 years later. And they had a slightly different interpretation of these 2-point functions. They showed that they kind of obeyed the right block decomposition of this BCFT. So this is sort of this picture that emerges here. If you study the subcritical brane, you have this what's now known as double holography. You have this nice structure that you don't just have two, but in fact 3 equivalent descriptions. One is where we do all our calculations, classical gravity with the brane. No, it's really not that hard to do these calculations. You have this BCFD description, which is the one that's well defined, right? It's UV complete. It's like a complete field tree. In principle, you can put on a computer, even so, of course, in practice, might still be hard to calculate. And you have this in-between thing, right, of gravity coupled to a CFT on half space, which from now on I'll call the bears, because that's how we call it these days. And back in the old days, we kind of felt like the first and the third description are really what's useful, and the thing in the middle is kind of mysterious and nobody knows what to do with it. That's going to turn out to be the major player in the applications for what people do today. The subcritical setting can be beautifully embedded in full string theory. It's much easier to do this than for the critical case. And sort of, let's start with the field theory to, where, take your favorite holographic CFT, n equals 4 Young Mills. You want to have a stack of these 3 branes and they live on half space. So somehow these 3 branes need to end on something. And if you want to keep as much supersymmetry around as you can in order to have control, what these 3 branes like to end on is stacks of NS5 branes and D5 branes. So all the stuff that's going on here, there's really one stack of 5 branes that's just all smushed together to a point. The only reason we kind of pull it apart is so you can see what's going on, right? They have like stacks of 3 branes, sandwiched between NS5 branes and D5 branes. These theories have been studied in all gory detail by Hanani and Witten and Gayotto and Witten. And what this really is, it's some complicated 3D boundary CFT, right? You could just impose Neumann boundary conditions on your D3 brane fields by putting like a single NS5 brane, but then you wouldn't expect this to be a holographic theory, right? What we want is to have a large number of 4D degrees of freedom, but we also want to have a large number of 3D degrees of freedom. So our BCFT is kind of a 4D CFT ending on a complicated 3D CFT. This is what the 3D CFT looks like. It's one of those quiver diagrams. The important thing here is it's characterized by 2 numbers, k and n5. And in the end, k over n5 will be the crucial parameter in the setting, where small k over n5 means there are fewer 40 degrees of freedom than there are 3D degrees of freedom, the other way around in the other case. That k over n5 is the equivalent of the tension in this bottom-up Randall-Sundrum models. Last but not least, this blue node, that's sort of the gauge tree that's living on these 3 branes. So this is, I have this gauge tree living on half space coupled to this gauge tree living in 3 dimensions. If you want to find the supergravity dual for this, you just look at symmetries. So I'm preserving a 3D BCFT, so right, the symmetries of a 3D CFT in my BCFT. I have an SU2 times SU2R symmetry. So I know my geometry has an ADS4 factor and 2 S2 factors, and you count 4 plus 2 is 6 plus 2 is 8, and you know you're in trouble. There's 2 dimensions here which are not constrained by symmetry at all. Everything you solve, right? All the form fields, the dilaton, the metric factors, they all depend on 2 variables. All the interesting physics happening on this Riemann surface sigma. You can use supersymmetry to get everything down to first order equations, but these are still highly nonlinear first order equations, and then you need sort of metric, or you need kind of Eric Doker, Michael Gutperle, and John Estes to kind of solve these differential equations. So it's really kind of artwork, but once this has been done for you, people by now know the most general supergravity solution with the symmetry. In particular, this is how this looks like, right? So everything happens on some Riemann surface sigma. You take sigma to be some sort of strip. Down this way is where ADS5 is hiding, so there's some asymptotic region where you see sort of ADS5 on half space. The other direction, my space sort of collapses, all the metric functions go to 0. So instead of having a brane on which space-time ends, I get sort of, this is just some stand-in for some internal 10-dimensional geometry collapsing to 0 size. And then sort of on the boundary, I have singularities which are associated to this D5 brane and NS5 brane sources that are in there. Okay, so the full supergravity dual is known, and unlike Hermann Verlinde's description of the critical brane, in this case, everything is known explicitly. There's nothing hidden in here. These are explicitly known supergravity solutions. So it's time for us to talk about massive fluctuations, not the ones that like a famous American statesman identified in our last election, but the massive fluctuations of the graviton again, right? We can do this exercise of the linearized fluctuations, and what you find in the ADS case is you again get a trapped graviton in the sense that its wave function is localized in the brane, but the trapped graviton is massive, right? You get a tower of massive modes, and you find that the lowest mode is parametrically lighter than all the other modes. So there's still some sense in which you get a trapped graviton, but even though it's parametrically lighter, it has a finite mass. And you might ask yourself, why is this happening? It's not just the cosmological constant. Like the de Sitter cousin of this, if you go to supercritical case, there's no mass there, right? And this is not just a feature of the bottom-up theory. It was also found in the top-down models that you also find this massive graviton. So I told you before, there are like two other equivalent descriptions. There's the BCFT dual. There's the intermediate picture with CFT plus Bass. And how do you understand the mass from these other points of view, right? Can we understand the mass in these other dual descriptions? And that's what I want to go through with you in the next 5 minutes. So let's first look at this intermediate picture. In the intermediate picture, we have a CFT plus gravity living on ADS4, but it's coupled to a Bass via non-trivial boundary conditions. And Perotti found already in 2002 that if in this theory you do a loop correction, you calculate the loop correction to the graviton propagator, the graviton picks up a mass. And Perotti showed in this paper quite convincingly that you should interpret this mass as a Higgs mechanism for gravity. If you look at the way the modes organize themselves, it's basically that same scalar that's running in the loop. That scalar gets eaten by the graviton and gives you a massive graviton where one of the polarizations of the massive graviton comes from the scalar that picked up some non-trivial expectation value was running in the loop. Why haven't you heard about this before, right? This sounds like such an important statement. A scalar loop gives a mass to the graviton. Why haven't we seen this all the time? Well, because it depends on the boundary condition for that scalar. If you impose the standard Dirichlet type boundary conditions for the scalar, totally reflecting boundary conditions for the scalar bounces off the boundary and comes back in, the loop doesn't give a mass. This is the one and only boundary condition in which the loop doesn't get a mass. Anything else, any boundary condition that corresponds to any sort of non-trivial communication of the scalar to something that's beyond the boundary, a Bass, will give this graviton a mass. Any coupling to a Bass directly drives gravity into a Higgs phase. If this sounds puzzling, let's for a moment talk about the analog case for a U1 global symmetry, where I think we're all much more familiar with this, right? Sort of, get off my camera. Okay. Let's study like a CFT which has a U1 global symmetry and has some charged operator W. Right? So one thing I can clearly do is I can just add W to the action and I'll break that symmetry. Obviously, the way this looks like from the bulk, I think we're all super familiar with, right? That W is dual to a charged scalar. H will sort of be the boundary value of the scalar. I force some non-trivial profile on the charged scalar. And so I just get Higgsing in the bulk. A scalar has a wave. The gauge field is Higgs in the bulk. You can do the same actually with gravity too. This has been shown by Blake, Tong, and Wei, that if you put like a holographic lattice on the boundary by the very same mechanism, you drive gravity into a Higgs phase right away. But what we are doing here with this coupling to the Bass is slightly more sophisticated. And this amounts to doing the same thing, but at the double trace level, right? You could take that same CFT with a charged operator W, and instead of adding W to the action, you add W squared to the action. That still breaks the gauge symmetry, but this time it's no longer a tree-level breaking, but this W squared just modifies the propagator of the bulk scalar field. Similar, you could do the analog of what we're going to do. You have two CFTs, each one of them has a charged operator. W1 plus W2 should have zero charge. W1 times W2 should have zero charge. But this thing violates like the U1 symmetry of each CFT individually. There's some overall U1 being preserved. But either way, this will violate the U1 symmetry of SCFT1 alone. And if you ask yourself how this happens in ADS, it's exactly the same diagram. Now, strangely enough, even though this is much simpler, it had only been calculated in the gauge field case 7 years after Perotti has done this graviton. But again, you find that the matter loop gives a mass to this time the photon. You would want to interpret this as saying this matter loop is really some sort of bilinear condensate in the bulk. There's like the scalar itself didn't get a wave, but the scalar bilinear got the wave. And again, you would interpret this as the standard Higgs mechanism. And the photon picks up a mass because it got Higgs by that non-trivial condensate. The U1 symmetry and the boundary got broken. Okay, so this is how you see the mass at the level of this intermediate picture. Let's here a few comments, right? This was a loop diagram. So the mass I pick up this way is of order G Newton, which is 1 over n squared. But on the Randall-Sundrum brane, we had n equals 4 mills living, right? We have n squared fields on the Randall-Sundrum brane. So the net mass you pick up in the RS case is actually n squared times 1 over n squared is of order 1. And that also agrees with the 5D calculation. The 5D modes gave me an order 1 mass for this trapped graviton. The scalar only got modified by boundary conditions, but for the graviton, I'm modifying the propagator everywhere. If you look at the effective action for that graviton, there's a Pauli-Fierz term emerging for that graviton. That graviton has an explicit mass term as part of, this is sort of in unitary gauge. Again, it's a Higgs mechanism, but in unitary gauge, you see an explicit mass term arising in the effective action for the graviton. This is not a subtle effect. There's an explicit mass for the graviton sitting right smack in your face. So, no, we see that the coupling to the bath drives gravity into a Higgs phase. And no, E and M, but gravity seems to be more exciting, so let's emphasize this some more. We can understand the same gravity mass also from the point of view of the dual BCFT. That's actually even easier. In the dual BCFT, we have a conserved stress tensor, but the conserved stress tensor is sort of the sum of the 4D stress tensors, what I like to call the ambient space, since boundary and bulk have been used already for the holographic stuff. So there's the 4D ambient space. I have the 3D CFT that defines the boundary theory, right? I have these 3 branes, stacks of NS5 branes. What's conserved is the sum of the two. What's dual to the 4D graviton is the 3D stress tensor. And the 3D stress tensor alone isn't conserved, so there's no more Ward identity that protects its dimension. The 3D stress tensor can, and in an interacting theory will, pick up an anomalous dimension, and that anomalous dimension is dual to the mass of the graviton. And we've verified this explicitly in like the D3D5 system that these anomalous dimensions happen. Now, of course, we did this at weak coupling, and the bulk calculates it at strong coupling. But you can explicitly see in the field theory calculation, you do pick up anomalous dimensions for these sort of boundary localized operators. And in fact, this argument is even much stronger than just the setting of subcritical S-branes. By this very same token, you can basically argue that whenever you have a graviton in ADS that's dual to a stress tensor out in the boundary, usually you would be saying the conservation of the stress tensor, you have a Ward identity that protects its dimension, that guarantees that the graviton is massless in the bulk. But the moment I couple it to a bath, right, all I need is this coupling to the bath. I need to know almost nothing about it other than it leads to non-conservation of the stress tensor. That's what coupling to a bath is supposed to do. Energy can flow to the bath. So the stress tensor is no more longer conserved, so it can, and in any interacting theory will, pick up an anomalous dimension, and hence your graviton became massive. So I think you can kind of argue this way quite generally. You can't have one without the other. You couple gravity to a bath, you drive gravity to a Higgs phase. It's a lot of unavoidable consequence. And you can make this quantitatively very precise. Right now you have to commit of exactly how you couple to a bath. There's a quite generic class of models you can get by, say, you have two CFTs. You couple them together via double trace deformation, some operator out of one CFT, some operator out of the other CFT. If both of those CFTs are holographic, then you can calculate the corresponding graviton mass using Parati's one loop calculation. In any setting, you can always calculate the anomalous dimension of the stress tensor of CFT1 using conformal perturbation theory. You get some complicated formulas which depends on the central charges of the two CFTs, the dimension of the operators, you couple together the dimension of spacetime, and you find perfect matching between this one loop calculation of Parati for the graviton mass and the anomalous dimension of the stress tensor over in the dual CFT. Okay. So all I've said so far, that's like 15-year-old physics, right? But that I thought is sort of important to review. What I now want to do in the rest of the talk is I want to ask myself how much of this applies to modern studies in black hole physics. Really, you might have wished that people who did those studies would have paid attention to what has happened 15 years ago, but of course the world doesn't work that way. Now, the black hole information paradox has dominated theoretical physics for decades. What happens if you take a sequence of bits, you throw it into this huge, dense black hole? Can you recover the information sometime later? Can you get that information back out of the black hole? No, in real life, that has been answered in the affirmative, but physicists have also made good progress on this problem. They demonstrated that using semi-classical methods, you can find the unitary evaporation of black holes. You can recover the page curve, just some fancy way of saying, yes, the information does come back out. We all probably heard about these major ingredients that went into this. There have been many talks at Strings about this. Let me not go into the details of this. What I want to kind of point out is if you look at the concrete implementations of how this has been done, the original work has been done in 2 dimensions where you take 2D gravity and couple it to a bath. The higher dimensional studies have all been done using the subcritical RS branes. either from the bottom up or more recently from the top down. And of course, this is all very impressive work. Like, for example, this latest paper by Christoph Uhlemann, that was, to my knowledge, the first time somebody has demonstrated a page curve in a genuinely 4D sphere of gravity that can be UV completed into type 2B string 3. Right? You know what the holographic dual is. It's n equals 4 3 mils ending on a bunch of 5 branes. But all these things were done in the setting of gravity plus Bears, and from what I just told you about, this means all page curves that we know to date have been obtained for gravity in a Higgs phase. And what I want to talk with you about in the rest of my talk is, first of all, I'm going to tell you how these calculations have been done, as I'm sort of just dragging you along. But then we want to kind of talk a little bit about, does this matter, right? Should I care about the fact that the page curves that have been calculated weren't really in a massless sphere of gravity, but was in a phase of gravity where gravity has been Higgsed? Okay, so this is how one does these calculations, right? So we have the the subcritical RS brane, the shaded region is gone. I kind of pulled the trick on you and flipped it over. So now this time my brain is on the left, no longer on the right. I hope you can handle that. Out here I have my non-gravitational CFT, right? So that we call that Bears. You have the brane. I want to put a black hole on the brane, so I need some sort of in the bulk a horizon which intersects the brane. To begin with, you don't really know what the horizon should do otherwise. But then, now you would be a problem in time-dependent GR. People don't like time-dependent GR, so they cheat a little bit. What they do is they, in addition, take this non-gravitating Bears and also put it at a finite temperature. This way, the whole system can be in equilibrium, but we'll see even in this setting, there's still some remnant of Hawking's information paradox. So that means I have a horizon far over here too. I have a finite temperature bulk horizon that extends all the way out to infinity, corresponding to the fact that the Bears is actually at finite temperature. The two are connected. That sounds like a minor detail. Mukund would tell you that's actually super important because that makes this a funnel, not a droplet solution. Mukund and others. And but let me not get into this. For people who know about RS brane black holes, so this works. Hawking radiation will be visible at leading order in n squared in the classical picture. And now what we want to do is we kind of say somewhere far away here in the Bears, I identify some region R, I call the radiation region, with sort of the spirit that any quantum information that escaped over there probably came out with black hole eventually, right? Things that come out of the black hole and go into the Bears, they'll end up in this radiation region R. So you want to calculate the entanglement entropy of this. Now, if I want to calculate entanglement entropies in sort of a quantum theory of gravity coupled to a CFT, I should calculate a quantum entangling surface. So really, from 4D point of view, that's like hard work. But the nice thing about these double holographic models is that sort of a QES in the 4D world maps just to a classical RT surface in 5D because the quantum effects of the 4D CFT were supposed to be dual to classical 5D geometry. So in the end, we just do 5D RT calculations. There are two RT surfaces. One goes into the black hole. The other one ends on the brane. If you look at the entanglement wedge of the surface that ends on the brane, the entanglement wedge contains some piece of the brane, including the black hole. That's what I would call the island, or what people call the island. Let's start with the Hartmann-Maldacena surface. The Hartmann-Maldacena surface is the one that gives the puzzle. If I kind of look at the Hartmann-Maldacena surface, it crosses the Einstein-Rosen bridge. And therefore, as the Einstein-Rosen bridge grows with time, the area of the Hartmann-Maldacena surface grows with time. So if this were all there is, you would find an entanglement entropy that grows linear with time forever. And at some point, it outgrows the Bekenstein-Hawking entropy of the black hole. And that's a puzzle for unitarity. If you understand the Bekenstein-Hawking entropy is somehow counting microstates of the black hole, you shouldn't get entanglement entropies which are bigger than the number of degrees of freedom we have available to you. Fortunately, we have this other surface. The island RT surface is, to begin with, much bigger than the Hartmann-Maldacena surface, but it stays outside the black hole horizon. It couldn't care less about the linear and time growth of the Einstein-Rosen bridge. Therefore, it's constant, and then overall you get a picture like this. The linear growth terminates at some time when you get a crossover to the island surface, and the entropy stays constant. Depends a little bit on parameters. In some cases, the island surface wins from the get-go and you just get a flat page curve. But for a large set of parameters, you get this, and that's sort of the page curve for gravity. But let me remind you, this is gravity in the Higgs phase. This is for a massive graviton. You can also directly interpret this in the BCFT as kind of dominance of the boundary channel versus dominance of the bulk channel in the operator expansion. So this is well understood also from the dual perspective. Does this matter? So last year we wrote a paper where we pointed out that at least standard law about how entanglement wedge reconstruction works seems to be somewhat at a clash with having islands in a massless sea of gravity. Let me quickly run this by you. This may well be the most controversial part of what I say. I hope everything else I said so far should be fairly uncontroversial. But no, if you have a sea of massless gravity and you have an island, the important thing is if you have massless gravity, I have a Gauss's law, which tells me essentially that any excitation in an island, I need to gravitationally dress out to the boundary. If I measure the metric near the boundary of my gravitational region from this near boundary behavior of the metric, I can read off the energy of the excitation in the island. So if you believe entanglement wedge reconstruction should work like this, you put some finite energy excitation in your radiation region, that should mirror a finite energy excitation over in the island, because the island is supposed to somehow be redundant with this radiation region. Then you're in trouble because you can discover this excitation out here in the complement of the island, but there's no sign of it in the complement of the radiation region. This excitation in the field tree is completely invisible to its complement. In the gravitational description, you can detect that excitation out from the complement, and that sort of seems to be in clash with the fact that you should not just be able to recover the radiation region from its entanglement wedge, but also the complement of the radiation region from the complement of the island. Wonderful. While this may or may not be a problem in massless gravity, it's very easy to see how this gets resolved in these holographic models of double holography. Because here I can put the excitation in the island and just gravitational dress it out to the radiation region through the bulk. I never have to pass this complement of the island. I do not have to gravitationally dress my excitation inside the gravitating ADS4 space. How come? It's exactly because you have a mass. What the mass does, it allows you to screen any excitation locally, right? The crucial effect of the mass, the fact that gravity is in the Higgs phase, means you break the connection between the energy in space-time and the asymptotic form of the boundary, right? In a standard sea of gravity, you can read off from the asymptotic form of the metric what is the mass you put in space-time. In the Higgs phase of gravity, you broke this connection. If you look at the constraint equation, the asymptotic form of the metric near the boundary is completely insensitive to whatever excitations you put in the bulk. Any excitation can be sort of locally screened. You no longer need to gravitationally dress excitations out to the boundary. So at that level, even a tiny mass makes a huge difference. That's sort of a yes-no question. If you're asymptotically far away, can you read off the total energy in space-time, yes or no? When gravity is in the Higgs phase, the answer is no. If gravity is massless, the answer is yes. Okay. Shewhart had a different way of saying this. He has kind of a more positive version of what actually does happen in a massless sea of gravity, right? And he would tell you what's really special about gravity, massless gravity. It doesn't obey the split property of QFT. The split property of QFT is a way of saying in QFT, you basically can define entanglement entropies more or less the same way. Take two density matrices, rho 1 and rho 2, and consider space-time like this. You break it up in two regions, R and R bar, but you keep some tiny color region out in the middle. There is a density matrix in the full space which looks indistinguishable from rho 1 inside and indistinguishable from rho 2 outside. It's more or less the statement that you can factorize ordinary quantum field trees more or less the standard way. Massless gravity fails to satisfy the split property, meaning in standard gravity you just cannot factorize the Hilbert space according to spatial location. And Shewhart would tell you that assuming the split property was the basic error in Hawking's calculation. No, he assumed the split property. It's not true. That's why he got a contradiction. What that picture would tell you is that what really happens in massless gravity is that all information is accessible all the time. So the conjecture would be that in massless gravity, you get a flat page curve. The entropy never goes up to begin with, so you don't have to worry about it how it comes down. This is not crucial at all for the rest of the story I've been telling you, right? I would still insist that so far we only know page curves in massive seas of gravity. This story would tell you this is probably really important because in massless gravity, quantum information gets localized very differently. But let me again highlight that the main player here is Gauss's law. Massive gravity gets rid of Gauss's law, and therefore it avoids all these complications, right? In massive gravity, presumably, you still have the split property. Different way of saying this is that the problematic assumption is that in a theory of gravity, you still go in and define sort of local operators, just like you would do in a quantum field theory. You can't do this. Local operators have to be dressed out to the boundary. Often we can ignore this because these ambiguities in how you dress, they go to zero as G Newton goes to zero. But to recover a page curve, we need to measure things with precision e to the minus s. And for black holes, e to the minus s goes to zero together with GE going to zero. So as you these ordering ambiguities or the dressing ambiguities are more important than the precision at which you need to know this page curve. If you couple to a bath, like everybody has done, you Higgs gravity and you completely get rid of this tension. You no longer need to worry about dressing because you can locally screen any excitations. In a massive sea of gravity, you do not need to locally screen your operator. You can locally screen your operators. You do not need to dress them to anything. This is what I wanted to say in sort of my review part. Now I was asked to end with a few comments about what I think are the open problems. I think probably the biggest open problem is kind of wondering whether you can actually get page curves, normal page curves like you would like to see them in a genuine massless sea of gravity, right? You might think that mechanism that people found so far, maybe the mass was just some sort of tool, maybe it's not important, the mechanism is so beautiful, maybe it also works in a massless sea of gravity. You might calculate the resistivity of a superconductor 10 times and think it's still zero in an insulator. You would be wrong in that case, but maybe it's fine here. Maybe by studying gravity in the Higgs phase, you can actually learn something about gravity in the massless phase. The first thing you need to do, you somehow come up with some sort of gauge invariant definition of what it is you're actually calculating. You could try to go after like defining local operators in a manifestly gauge invariant way by doing something relational like this, where you integrate over all space-time and try to tag operators by, say, things that are localized in the high curvature region. That tends to give you very non-local things, especially in these eternal black holes. Maybe in like strongly time-dependent backgrounds, it would be okay. The other thing you could do is maybe you work directly, right? No, you accept that you need a gravitational dress things to infinity, but different dressings differ by order G, but maybe if you commit to one, maybe one can define something that gives you the right precision to calculate this. I think the main objection that, again, this is sort of, I'm channeling Surratt here, but the main objection Surratt would have against this is it's easy to define something where the page curve goes up, right? If we throw anything into a black hole, we're never going to see it again, right? Losing information is really, really easy. But if you want to have the exponential precision to see what's actually come back out at you, those observers might already have enough power to see the full quantum state to begin with and never see entropy to go up. But this is, I think, an open question, and would be interesting to find an answer to this. I know that the talk that Dan gave us yesterday says like in this tensor network, you can do it, but that doesn't even have gravity in there. So maybe if there's really some subtlety of whether gravity is Higgs or not, I'm not sure if you see this in the tensor network. The second thing you might wonder about, since this intermediate picture was so crucial, can we maybe come up with some sort of more complete definition of this intermediate picture, right? That was sort of the most iffy piece in the whole puzzle. We have a BCFT, we have gravity, and then we have this halfway thing. The halfway thing has some actual problems which have been pointed out last summer by Omir and Wei, in that it allows shortcuts, right? In the intermediate picture, you want to have gravity on the brane, fields you out in the boundary, and you can easily convince yourself if you compare like a path that goes along brane and boundary, it's longer than a path that cuts through the path. So this naive picture of the intermediate picture is probably incomplete. In the limit that I push the brane off to the boundary in this near critical limit, it's probably fine. There has been a dictionary proposed by Dominik Neuenfeld. Christoph Uhlemann, Hao-Yu Sun, and I, we believe we have a very precise definition of this intermediate picture, but it would actually look a little different from the intermediate picture people use all the time. But what we want to make precise is basically the notion that what you did in this intermediate picture is you dualized the 3D CFT, but not the 4D CFT. And while in the RS brain world, this was just some sort of hand-wavy motivation, you can just actually do this and define a well-defined intermediate picture, right? We had this complicated 3D CFT. It was coupled to n equals 4 Wilson half space. You can take just this 3D CFT and chop it off by having like these D3 branes end on a bunch of D5 branes. That way you created a 3D CFT which has a global SU n5 times k symmetry instead of the local one it had before. And once for this 3D CFT, you can easily find a holographic dual. That's again one of these UCLA solutions. This time it's a wedge instead of Mars setup. But you created an ADS4 dual which has a global SU2 and FK symmetry. And now you can by hand couple this to n equals 4 super Young mills, right? You have a dual which has a global symmetry current. That global symmetry current you use to gauge it and couple it to the n equals 4 field. So there's an intermediate picture that I believe one can very rigorously define. It doesn't have any problems with shortcuts, but it looks a little different from the intermediate picture people like to use. I think for the page curve calculation, this is not a problem whatsoever, because the intermediate picture was just an excuse of why I want to calculate these 5D RT surfaces. And for that, I think the only thing that's important is there is a well-defined intermediate picture, not how it actually looks like. But it would be interesting to explore this a little bit more. What exactly is the connection to these Randall-Sundrum spacetimes as people have been using them before? Last but not least, I think it would be interesting to connect the story I've been trying to tell you to this recent discussion of the algebraic approach, right? In work by Leuthäuser and Liu and by Witten, we've been told that in the large N series dual to like an ADS black hole, we have this interesting algebraic structure emerging at very large N, where you have a CFD A right zero and a operator algebra A right zero and A left zero, which corresponds to like is the boundary version of local quantum field outside the horizon. And then the full right and left algebra also have the central element AU, which is sort of shared between the left and the right, but is central to both. You might ask yourself, basically, the whole point of my talk is if coupling to the Bears is not a harmless enterprise, right? Coupling to the Bears completely destroys the structure of massless gravity and drives you into a Higgs phase. What does this look like from the algebraic approach? Problem is, I don't understand any of this, but the one calculation I can do is I can show you that this operator U, which essentially was the Hamiltonian divided by N, U fails to commute with these algebra A right zero and A left zero, even at leading order in large N when you couple to a Bears. So this entire algebra structure just breaks down completely the moment you couple to a Bears. What does this have to do with islands? I don't know yet, but will surely be good to understand. I think one way you surely should still be discovering type 3 algebra and the full coupled thing of CFT plus Bears plus coupling. Maybe what this is saying that if you want to get local fields in the bulk, you need not just the CFT, but you need CFT plus Bears, and that's sort of the inverse statement about the island, right? If you want to describe physics in the island, you need something that's sitting out in the Bears as well. You need the radiation region. But exactly how to translate this statement that U no longer commutes with the story about islands, I don't know. So interesting open question. I think I finished perfectly on time. So with this, I'm open for like polite, nice questions. And
All right. Done.
Thanks for a really beautiful review, Andreas. I just have a comment about the things you said about the dressing and massless gravity. And I want to push back a little bit on this idea that observables have to be dressed to the asymptotic boundary. For example, we could be living in a closed universe, and then we would like to still have some observables, or even in an open universe, we don't actually go infinitely far away when we do experiments. And in particular, in the context of the island, I think the natural way to think about, so what you do in those situations is you dress relative to some feature of the state, right? Like what Edward was saying in his talk yesterday. And I think for the case of the island, the natural thing to do is to dress to the infalling shell that created the black hole. So instead of trying to run the Wilson line out into the black hole exterior, you run it in to the shell. And then you're defining an observable that only makes sense if the shell is actually there, right? So it's a more restricted observable, which is the kind of the price we have to pay for doing things without a boundary. So, intuitively, it's like you can imagine something that, it creates something near, inside the black hole, but then decreases a bit the energy of the shell that made the black hole. And so then the asymptotic energy doesn't change.
I have no objections to anything you said. Not sure. It might well be that a story like this goes through. I don't think nobody has done that yet, right? It would say you actually have to study black hole with some infalling matter, so you can worry about that stuff. No, in the massive zero, you don't have to worry about dressing. That's I'm more confident about. If I worry about dressing, do I get or do I not get page curves? I think that's an interesting open question.
You're still doing dressing in the massive theory. You're just dressing to the head of the condensate. Right? But, I mean, you still
right, but locally, right? I had some excitation here, and basically I'm dressing it to its immediate surrounding. the charge gets screened right away. It's a local dressing, locally at the spot. No matter where you insert your source, you can dress it like locally right away to the condensate because the condensate is everywhere. You don't need to dress it to somewhere else. So it's definitely much easier to work with a massive sea of gravity. And people only work with massive seas of gravity for page curves, so clearly it was easier for most people to do that.
Right. Yeah, I mean, you still have to do diff invariant observables.
Right, but it's not a problem getting diff invariant observables in the Higgs phase.
Yeah, so the islands and the entanglement entropy is a property of the state. So we can prepare the state as usual, and then we can decouple it before we do the computation of the entropy. And so couple it, we have massless gravity, and then we still have the island.
Okay, let me try something here. I think I'm supposed to be able to get a control T. Do I get some screen? No, it didn't work. Okay, let me just try to... No. Supposedly I can draw on here, but let me try to say it in words. Right? If you do this, right, if you go from like a massive phase to a massless phase, you get a shock wave coming in. Where inside the shock wave it's massive, outside it's massless, and it's not. No, you can look at the island, and you can draw cartoons to yourself where the islands will always stay in the massive area and will kind of hit the singularity before it gets out into massless region. But no, one should check this. It would be amazing to me if the island could survive going out into the massless region. But I think unless one actually studies the switching it off, it's not obvious that the island will ever leave the massive region, right? You have like the shock wave coming in and it's inside it's massive, outside it's massless, and it's easily conceivable that the island stays always in the massive area.
I'm not sure it makes sense to talk about this massive region in the interior. I mean, are we living now in massive gravity or in massless gravity? I mean, there is matter around us, right? So,
okay, in flat space, I haven't talked about it. In flat space, you cannot Higgs gravity because the limit of a massive graviton to a massless graviton in flat space is completely discontinuous, right? If you take a massive graviton, take the massless level, you end up not with a massless graviton because you always have 5 polarization in the massive graviton. You have 2 in the massless one. That's this VVDC discontinuity. So it's something very special about ADS space. ADS space doesn't have the VVDC discontinuity. The graviton propagator in ADS space has a smooth limit, and there we can talk about this. So in the space around us, I'm confident we have a massless graviton because we see 2 graviton. Well, we believe the graviton has 2 polarizations, not 5. And I guess LIGO saw gravity waves. I'm not sure if they can tell whether it had 5 polarizations, but I think things would go wrong with 5.
Thank you for a beautifully clear talk, Andreas. So I just want to make a comment. The fact that you showed that massive gravity is kind of unavoidable on the boundary CFT that you wanted to consider is related to resonates with the swampland condition that you cannot consider coupling arbitrarily large n quantum field theory to gravity. That should fail. And so I would interpret your statement that the massive gravity should emerge as a resonance of that fact.
Cool. I like comments which support what I'm saying.
All right, any more questions? Emil.
Yeah, so is it fair to say that the reason you're getting some massive graviton is that your bath essentially has as many degrees of freedom as the lower dimensional, boundary theory that you're trying to study? But in other words, I
think that's really important, right? If the bath had much fewer degrees of freedom than the boundary, it's sort of, okay, now people got me a screen, now my talk is gone. The statement I made in the end, for example, the algebraic approach that U gets kind of fails to commute already leading level, I assume I have a large N CFT for these calculations with Ofer and Adam, where we showed like the matching between the one loop calculation, the conformal perturbation C, I needed a large N bath. And that's exactly what you're saying. I think if my bath had only order 1 degrees of freedom, whereas my gravity has order N squared degrees of freedom, I can't stuff enough energy into the bath. And in 2D CFTs, there's a paper by people whose name I forgot, but people showed rigorous bounds and so the transmission coefficients in 2D interface CFTs that it goes by the ratio of central charges. We have one very large central charge theory and one very small central charge theory. The transmission coefficient is limited by the ratio of the 2. So I think in 2D one can make this very precise, but I think in higher dimension I would expect the same thing. Unless both of them are large N CFTs, I wouldn't get significant energy transmission. I would suspect the mass being suppressed by the ratio of central charges.
But I think the point I'm trying to make is that originally the idea of coupling to a bath is you want to mock up the nexus between an ADS throat and flat space. And that coupling happens only through single trace operators that have just a few degrees of freedom. And so that original way of saying, let me have some way of having energy leak out of the CFT into an auxiliary system seems to me very different from...
Right, and people study that too, right? There are papers by, I think, Marcus and then Mark van Ramstong, where instead of having these double trace couplings that I mostly look at, which are via boundary conditions, you basically can go into this 3-band, 5-band system. You have n equals 4 mils, and you have a bunch of sort of small gauge groups in the middle. You have fewer 3-bands in the middle, and you have another n equals 4 in the other way. So then it's always kind of direct gauge couplings between like half space and half space. So there are various ways you can couple to the Bears. I agree with you. The boundary conditions aren't the only one. My understanding is that's what people actually do, right? You take gravity and ADS, you couple via boundary conditions. You can do it in different ways. That's why I thought this argument about the anomalous dimension is so powerful, because that doesn't care at all of how you couple. You couple any way you want to a Bears. As long as energy can leak, the stress tensor is no longer conserved and the graviton will get massive. I don't think there's any way around this, no matter how you couple. These boundary conditions sort of speak to this loop argument of Paratis, but I think that anomalous dimension argument, that's just true no matter how you couple to the Bears.
Okay, I think we need to wrap up there. So, yeah.
We didn't get the triple ping yet. No, let Dan Harlow attack me one more time.
I just wanted to make a very brief comment. So I think part of this issue about there's a mass, there's not a mass, has to do with the fact that usually what mass really means is it's some Casimir of the Lorentz or conformal group. And here the symmetry is broken. So then we can kind of get into these kind of fluffy discussions about whether there's a mass or not. I think what would be really convincing is if there was a mass that was large in ADS units, but if I understand that's not the case.
I think Gauss's law is a very clear statement. The fact that can you read off the mass of total mass of spacetime from the asymptotic fall-off of the metric, yes or no? That is more than just some numerical accident about Casimirs. That's like a yes-no statement. In the Higgs phase, the answer is no, you cannot. And in the massless phase, the answer is yes, I have Gauss's law. I can read off the total mass of spacetime from infinity. Again, whether this matters for quantum information, maybe that's an open question, but I think it's a very important difference that is not completely trivial.
All right.
Thank you.
Yeah, let's all thank Andreas for a wonderful talk.